Hey guys, thank you so much for being here, and let's start our third meeting.
Right, so we're going to start with some review, especially for the new students. And you can refer to our presentations and some of our previous videos on the V Clubs page. So here are some general club information for the new students. We have Tuesdays 8:20 to 8:50 are our timings. And we're going to be doing some demonstrations on the concepts in SAT and AP physics and in quantum physics as well. We're going to learn about the interesting concepts in physics. We're going to demonstrate some keen interest in physics, right? And develop some strong scholarship of the subject. We're also going to use molecular workbench from time to time for animations and models demonstrations. And we also have some links for the recording for last meeting, and that's the link to our YouTube channel. You'll have like a copy of this presentation afterwards, so you can access. So here's a review of black body radiation. And so we have the idea of a black body which will absorb and emit electromagnetic radiation. And so people were trying to make like graphs of this and solve the problem of black body radiation. We talked about this a lot last time. But essentially, Planck solved this problem by predicting that atoms could only vibrate at integer multiples of frequency. And that became referred to as Planck's constant, right? So he analyzed the black body spectrum to arrive at this. And so we have Planck's relation here, which says that our energy is equal to Planck's constant times the frequency, right? But if you remember, frequency times wavelength is wave speed. So for the frequency, we can substitute your speed of light divided by the wavelength. And so you get this relationship, h times c over wavelength, where c is the speed of light. And so it's a key origin to quantum mechanical ideas through its connection to the photoelectric effect, which we'll be covering right after that. Here we have your electrons released from the material when it absorbs the electromagnetic radiation or light. So you can see in the top left photo, you can see that the light, the kinetic energy from the light, right here is causing the electrons to leave the piece of metal, right? And so in the top right-hand corner, you can see how the sunlight is hitting this positively charged plate. And because of that, the electrons are flying off, right? To this negatively charged plate. And so what's happening here is that there's a current induced. And so you can see if there's a current meter right there to your right, then that's going to read a current. There's a current flowing through this. And that's the key idea behind the photoelectric effect. The energy of the charged particles is determined by the frequency of light. And so here Einstein observes that it takes work to pull the electrons off of the metal. And so in the bottom left-hand corner, you can see that plot of how that essentially works for different metals, like rubidium and potassium and sodium. And so the slope is actually Planck's constant, and that is the key tie-in right here, how both of these experiments are tied together and are a very key foundation for quantum mechanics. And so now we're going to show a quick demonstration of the photoelectric effect via molecular workbench. And so this is molecular workbench. And so we'll browse the entire library and then go light and radiation. And then here you can see the photoelectric effect demonstration. So this is the demonstration. And we're given the choice to alter the wavelength. And there's a certain threshold for the wavelength from which our electrons will start flying off. So if I go to the far right and I choose infrared, you'll see that here there are the waves, but nothing's actually happening here. There aren't any electrons. So we can try to up it a little bit. So as now we have yet. Keep going. So here you can see now we're in the visible light spectrum. And here you can see now the electrons are flying off. So there's a certain threshold of the wavelength which causes those electrons to fly off. And so this is just a nice demonstration of the photoelectric effect, how light is causing those electrons to fly off the piece of metal. And as you can see, it depends on the wavelength of light. It's showing above right there. So that's a quick demonstration. So if you want, you can access it through your molecular workbench software, if you have that on your machine, which we have some instructions for that on this slide right here. You get the latest version of Java and you can go to the website. So here's a quick recap. So Planck's ideas and Einstein ideas were the ideas of quantum mechanics, key ideas. and they can't be derived from Maxwell's equations, right? They were the ideas of the particle theory of light. And so Einstein had the idea that light is composed of photons, right? And that cannot be explained by the double slit experiment. And so light has the wave particle duality, right? And light as a wave can be explained by the particle theory as well in certain experiments, right? So we have the wave particle duality. And so this shaped the whole structure of classical physics. This was completely revolutionary, right? And so there were new discoveries made. And also the boundary between the particle and the wave became a little more vague. So here's the physics news. Hopefully you remember this from last week, if you were here last week. So this is the link to watch the video. We won't be watching it again, but here's a quick summary. We have the researchers at EPFL, and they trapped the light on the tiny metal wire as a standing wave. That's what they did. And then they shot stream of electrons past the wire, holding the trapped light close, such that the photons and the electrons, they were like forced to interact, right? And so in the interaction, there was an exchange of quanta, which was observable by the special microscope. And so in this way, they were able to see an exchange of energy along the wire, which allowed them to take this photo. And so here you can see in this experiment, they were kind of able to exploit the wave nature and the particle nature of light to take the photo. Because they show light as a standing wave, but they also use its particulate nature regarding the stream of electrons.
So this is our physics photos of the day, and maybe you have observed this when you observe like soap bubbles, and on the right there's like oil on the ground, and this is called so this is a optics effect. It's when there's a soap bubble, it has an upper layer and a lower layer, and in the middle is air. Whenever light enters a different medium, it interferes, and this is called film interference, and create this beautiful light. It's called iridescence, and this is basically different medium causes different kinds of refraction, and you like see different colors. When you move around, like on the ground, you will see different colors because different colors that are at different wavelengths. And so this physics photo on the right is from a winner from physics photo contest last year. This is probably what we're going to do, and we will introduce it later in the year. All right, so single photon interference. If you remember double slit experiments, is pretty much a redo of that, but it's using single photons. So since people came up with the idea of quantum, and they think about what happens if there's like very dim light, and if there's only one photon past the slit, would it still have that wave properties? And turns out it does. So in 1907, one scientist used very dim light and basically just enough energy for just one photon, and this still caused the interference pattern we observed. So you can think of it like one photon interfered with itself almost. So what this means is that when he passes photon one time at a time through the slit, the cumulative pattern is still like still has that interference pattern. So on the very right, you can see this is how the pattern occurs over time. Yeah, and we'll get like next slide will enter like, what happens behind the scenes.
So today our main topic will be matter wave. So if we want to talk about matter wave, we need to talk about the person who first come up with this idea. The person, his name is Louis de Broglie. He is from a Duke family of France, which means his father, his grandfather are all dukes. His grandfather, I remember, used to be the prime minister of France. So in 1924, he published his professor degree thesis, and which he postulated that the the property of the electrons, particles like electrons also demonstrate wave properties and suggest that all matters have this property. So the way he did this is that he borrows and elaborates Einstein's idea of photon, because since photons has wave particle duality, he considered that all matters have wave particle duality. And after this his idea is tested and proved, he wins the Nobel Physics Prize in 1929. So this is a small fictional story about how he come up with his thesis, and it is not true, but it's really funny. So so it's said that de Broglie he used to be like a soldier he used to be in army of France. So one day he saw that the radio he is very interested in physics idea like radio wave. So when he's writing his thesis, he checks many ideas of great physicists, and he just and when he's playing with the equations, he just come up with this idea that the that by plugging in different equations, he can get a wave function for particles like electrons. And he just but he only writes 2 pages on his thesis. So he give it to his teacher, and his a teacher doesn't like the teacher doesn't really agree with this 2 pages thesis. But since he is the Duke of France, his teacher cannot say anything about this. So his teacher come up with an idea and send this letter to a famous scientist Einstein. It's right, and writes like, Einstein, dear Mr. Einstein, please check out about this letter. And Einstein just checked it, and and during the letter, his teacher advertently points out that, oh, this, by the way, this student he is the Duke of France. His grandfather used to be the Prime Minister of France, so he will be very welcome if you want to come to France. So Einstein is really clever, so he writes a recommendations, and therefore de Broglie passes the PhD. And of course this is a fake story, but Einstein did. He really appreciated de Broglie's work. And remember, all science idea like this requires a long time of thinking and doing and of thinking and communicating. It cannot be just come up like in a single day or in a short period of time. So the equation. So how did de Broglie get this equation? So first, he has the light speed, the c equals the wavelength times frequency. This is a fundamental principle of wave. And another is from the energy. So Einstein's photoelectron effect suggests that E equals hf, and another famous equation is that E equals mc squared. And also it is proven that and since momentum equals mass times velocity, in this case it would be light speed. So doing some small, so you just plug in different equation, you can get the equation on the right, which says that the wavelength equals Planck constant divided by momentum. So here, if you substitute in V equals C, and C equals the lambda times frequency times wavelength, and M for E equals mc squared, and what will you get? This is quite complicated, so I'll just point it out. What you'll get was the frequency of the D. Frequency equals E divided by H, which is correct, which is just the equation which is just the Planck equation for photoelectric effect.
All right. So we got like if we plug in the equation, we get Planck's relationship we went through at the start, and that's pretty cool. And then after de Broglie, he had this theory of everything matters. We can see matters as waves. Um, this is the subsequent experiment that proved it. But the funny thing is, the scientists were actually trying to do something else, and they had no idea what quantum mechanics was. So two scientists named Clinton Davison and Lester Germer, in 1927, like 3 years after de Broglie came out with his theory, and 2 years after he won the Nobel Prize, and they were these two scientists were studying the surface of nickel. Um, they um, they were trying to eject electrons and see where the electron bounce out, so they can deduct like what the surface of nickel is like in a microscopic scale. And this is like the idea of in physics, when you're trying to observe something, when it's really hard to observe, uh, you manually eject something and hope to get something in return. So they have this setup. They have a, a gun at the bottom left, and they have a vacuum chamber contains the target, and they have this detector receiving the diffracted electron. And so during the experiment, they had a little mishap. Some oxygen went into the chamber and form an oxidized surface on the nickel. So they had to heat up the thing, and in chemistry that would decompose the like the oxides. So when they were cleaning the surface, they unknowingly formed another compound. They formed a polycrystalline on the surface of nickel. And what it turns out is that they observe a diffraction pattern with the electron, with the movable detector like we've seen in double slit. But this is nothing like double slit. So then they went to a conference and learned about the very recent development in quantum physics. They learned about de Broglie, and then they thought about it. Um, could it be interference? Um, so then they realized that the polycrystalline that it formed on the surface, and it turns out somebody had proved before these atomic structures, they would actually act as a diffraction medium. So like if you have studied chemistry, you know that some atoms have very particular structures, and these structures would cause um, like um, in this case it caused a diffraction. So they actually achieved a double slit without actually using the double slit. They diffracted. They found out that electrons also has this wave property that will diffract, and they did the calculations, and what they said is that the result almost matched perfectly with what de Broglie came out. So this was the experimental proof soon after de Broglie. But the thing is, because double slit is a very hard experiment to do, you have to have very thin slit, and the light has to have a particular wavefront. So the real double electron interference double slit actually came out later, which we'll see later.
So here is the electron interference double slit experiment that proves the Broglie's equation. So since electron is a particle, so usually if we fired particles, if we assume particles are just like small balls, we fire them through through some slits, it will only create like two lines of particles. But waves, however, can create interference patterns. So I remember it's 1961, a scientist fires a beam of electrons through the double slit, and however the slit after they go through the slit, an interference pattern is shown. And later, scientists have this idea that maybe it's because that too many electrons are fired at a single time, so they just decided that they should fire one electron for a single time. And what and magically, like, even if there's only one electron, there's also such pattern. So basically, and one electron, it interferes with itself through the double slit, which is kind of amazing. And another thing is, even more amazing thing is that when scientists they put detector on each slit to determine which slit does the electron pass through, and then the interference pattern just magically disappear. This is a phenomenon we are going to discuss like in our later topics. So here is a timeline of how this wave-particle duality is discovered. So at first, in 1901, Thomas Young conducted the first the double-slit experiment to light that proved light is a wave. And in 19, the Planck's law came out in 1905. Einstein published photoelectric effect that shows that photon is a particle. And then in 1907, it's the single photon interference. And then comes the electron diffraction and electron interference and single electron interference. Then in 2003, scientists actually proved that bigger molecules, the C60 fluorine, which consists of 60 carbon atoms, and it can also have this. It can also demonstrate the wave property when it goes through a double slit experiment. So what's the explanation for this? So the physics nature behind the matter wave is a controversial topic. So some consider that only wave is the real nature of the electrons and photons. Some consider only particle is. The other part is just an emergence property. So if you guys don't know emergence property is that when many small things combine together, it creates a whole body. Like humans are made up by different cells. Each cells are just cells, but when they combine, they make a living human. So an interpretation to the Copenhagen interpretation, we'll talk about this later. It is an interpretation about like what's the reality of this quantum physics ideas. It points out that the nature of wave particle is impossible to be determined. It is not bounded by like scientific knowledge. It cannot be determined. And I choose this photo in the right because what you see that if you shine two light in two directions of the object, it shows different property. And that's probably in the truth of this wave particle duality. Its real nature still remains unknown. But when you look at it in a different perspective, it shows different like patterns.
So we have some upcoming topics. So we talk a lot about light, and there are also we've most focused on like the wave parts that relates to property of particles and the particle properties that we can relate that to wave. But there are really a lot of topics, and one of them is electromagnetic waves, because light, we can see them as ENM waves. And so will be topics in polarity, um, and we can learn about topics in ENM, such as right-hand rule, through those topics. And then we have a lot of stuff left in quantum realm, like the Copenhagen principle Alex talked about. It's really why, like, when we trying to determine which slit the photon pass through, the interference pattern disappear. We will talk about those, and the uncertainty principle, the EPR paradox, and we also have some application like quantum computers. So that will be like another two sessions. And then we have special sessions about relativity, and we'll have Boholm present for us. Then we will introduce physics photo contest, and we will also have try to have interesting activities like Kahoot, and we can also watch videos. So yeah, I think that concludes our meeting. You can find all our resource, includes our slides, the download to Molecular Workbench, and access to recordings and everything on our vClubs page. So be sure to check it out if you want to revisit our meeting materials. And thank you and have a great day.
Thank you.
Well done, guys.
Thank you, everyone.
Mr. Nelman, stop the